Hello guys, welcome once more to another video in our YouTube channel. So in today's video we look at June 2022 further maths paper 3 detailed solutions. So let's get started. Alright, so we begin with question 1, which is from the topic system of forces and equilibrium. The question reads: a rigid body is acted on by three forces F1, F2 and F3, where F1 is 14I plus 8J plus 8K newtons, F2 is 9I plus 4J minus 12K newtons, and F3 is 24I plus 8J minus 9K newtons. The force F1 acts through the point with position vector negative I plus 2J plus K. The forces F2 and F3 act through the point with position vector I minus J plus K. The system is equivalent to a single force F acting at a point 1, 1, 0 together with a couple G. Find Roman 1, the force F, Roman 2, the couple G, and the Roman 3, a Cartesian equation of the line of action of F. Alright, so upon analysis of the equation, we have been told that the system is equivalent to a single force F acting at this point together with a couple. So we need to note the conditions for a system of forces to reduce to a single force together with a couple. So if it reduces to a single force, then the first condition is that the sum of the forces of the system is equal to that single force. That is, it is different from 0. And the next condition is that the sum of moments of that system is definitely different from 0 as well. So to find a single force, we just need to sum the forces of the system. So our single force is the sum of all the forces F1 plus F2 plus F3. We just need to write the forces in the column form, meaning writing the vectors in the column form, adding the corresponding entries and deducing it as a vector. So the single force F is 47I plus 20J minus 13K. Now the next question is asking us to find the couple G. There is a very important statement here which says that the system is equivalent to a single force F which acts at this point together with a couple G. So since it reduces to a single force together with a couple, it means that the sum of moments, that is the sum of moments of the system, is just equal to the moments of that single force and the couple. Remember, a couple is the moments actually. Okay, so we have that the moments of the system is equal to the moments of the single force plus the couple G. So from there we can easily get our couple G, which is taking the moments of the system minus the moments of the single force. We are using this because it said the system reduces to a single force together with a couple. So the sum of moments of that system is not 0, and it is just equal to the couple alongside the moments of that single force. So we just to find the missing terms. So we have to find the moments of that single force, which is R cross F. So we use the determinant method. The R is simply the position vector of the points of action of that single force, which is I plus J plus 0K, and then the single force itself is 47I plus 20J minus 13K. If you do the cross product perfectly, you're going to get negative 13I plus 13J minus 27K. We are now left to find the sum of moments of the three forces that made up the system. So it means we take R1 cross F1 plus R2 cross F2 plus R3 cross F3. If you do it perfectly, you're going to arrive at 17I plus 84J plus 19K. So our couple, which is G, is just equal to this 17I plus 84J plus 19K minus negative 13I plus 13J minus 27K. Doing it correctly, we have that a couple G is 40I plus 63J plus 36K. If we're asked further to find the magnitude of the couple, we just find the magnitude of what we have here. Alright, so the last part of the equation is asking us to find the Cartesian equation of the line of action of F. So it should be noted that the Cartesian equation of the line of action of a force is simply the position vector plus a parameter times the direction vector, and the direction vector is a force itself. Okay, so our arrow here are all points on that line, and then our small arrow is simply the position vector of the line of action of the force, which is I plus J plus 0K, because the force was acting at a point 110. So with that said, it means r is equal to 110 plus lambda into the force, because the force is the direction. Okay, so we have 47, 20, negative 13. So we can replace r with xyz, and then now we equate corresponding entries. So x will be equal to 1 plus 47 lambda, y will be equal to 1 plus 20 lambda, and z will be equal to 0 minus 13 lambda. We make lambda the subject of the formula in every equation, and then since lambda is the subject of the formula in the first equation, in the second, and in the third, it means that those equations are the same, so we can equate them together, and this gives us the Cartesian equation of the line of action of the force F. Alright, so let us move on to question 2, which is talking about oscillatory motion, that is simple and damped harmonic motion. The question reads, a particle P of mass M moves along OX under the action of a force of magnitude 4m omega squared times the magnitude of x directed towards O, where omega is a positive constant. The resistance to the motion is 2 lambda m omega times the magnitude of v, where lambda is a constant and v is the velocity of the particle P. A. Show that x dot dot plus 2 lambda omega dot plus 4 omega squared x is equal to 0. Discuss the motion of P when lambda is 0, when lambda is 1, and when lambda is 5 on 2. So that's a B question. Alright, so let's analyze the motion together. So the first thing is that the particle moves along the OX, meaning along the horizontal axis. So this is O, and then now it is moving to the right. Okay, so we have the particle there. Here is the origin, here's the particle. It is moving such that the magnitude of the force that takes the particle to the right is actually acting towards the origin. So it means that the force is acting towards this direction, and also we have that the resistance also be acting in the opposite direction, because the direction of motion is to the right. So we are going to apply Newton's second law of motion, which says that the resultant force in this system is equal to the mass times the acceleration. Since there is no pulling force, it means the force taking it to the right is 0. Now we have two resistive forces. Okay, we have we have a resistive force, and then now we have the retarding force. The retarding force is given by 4m omega squared times the magnitude of x, and the resistive force is given by this. So we have 0 minus the sum of those two forces, because they are in the same direction, to be equal to the mass times the acceleration of the system. So it means that we have we can divide all through by the mass, and we arrive here, knowing fully well that v is the velocity, is simply the change in displacement, because x is a displacement, and a is the acceleration, is a change in the velocity, or the double change in the displacement. So with that said, we just need to replace x here with x, we replace v with x by dt, and we replace the acceleration with d squared x by dt squared. We simplify the equation, and we should note that d squared x by dt squared is x dot dot, the x by dt is x dot, and x remains x. So this is what we were required to prove. Now the second part of the equation, we are now discussing the motion of the particle P. So to discuss the motion of the particle, first we have to express the displacement in terms of time. So to do that, we need to solve this second order differential equation, and it is clearly homogeneous because the right hand side is 0. To solve this second order differential equation, we have to start by finding the auxiliary equation. What is the auxiliary equation? We choose a parameter alpha, so this term here becomes alpha squared plus 2 lambda omega. This term becomes alpha plus 4 omega x plus 4 omega squared, and this term here becomes alpha to the power 0, which is simply 1. So we have our auxiliary equation to be this. Now we need to solve for alpha because it is a quadratic equation. We use the quadratic formula and simplify, and we get our alpha to be omega into negative lambda plus or minus the square root of lambda squared minus 4. Now to discuss the motion of this particle, we need to use the conditions that have been given. For lambda equal to 0, we can get alpha. Our alpha will be plus or minus 2i omega if we simplify perfectly, because 0 will be here. 0 squared minus 4 is negative 4, and the square root is 2i, but there is an omega multiplying it, so our alpha is plus or minus 2i omega. Now we are going to write the general representation of the displacement when lambda is equal to 0. So having the complex roots as plus or minus 2i, it means the complementary function or the general solution already is just a cos 2 omega t plus beta, where beta is a constant. So from there we can now discuss the motion. So the first thing is that the motion of the particle is oscillatory because it can be written in the form it can be written in the trigonometry form. Let me specify it that way. Okay, now this cos 2 omega t plus beta is called the oscillating factor because it is what is making it to be sinusoidal, and this a here is called the maximum displacement or the amplitude of the motion. So it is oscillatory. Why? Because it passes through the equilibrium position many times. Now the next thing is that it is simple harmonic. Why is it simple harmonic? Because it can be written in this form. Okay, and since it is simple harmonic, we can now deduce the period of motion. The period is 2 pi divided by the coefficient of t. In fact, 2 pi divided by the imaginary part of our complex solution. So 2 pi divided by 2 omega becomes pi divided by omega. So that is a period of our motion. Now in the second case, we are dealing with when lambda is equal to 1. When lambda is equal to 1, we need to replace 1 here and simplify. We get alpha to be, if you multiply inside here by omega, we get negative omega plus or minus omega root 3 times I. So the general solution is going to resemble this form: a e raised to the power negative omega t, the cosine of root 3 omega t plus beta. Beta and a are constants. Now since the motion can be written in this form, first of all it is oscillatory, and this cosine of root 3 omega t plus beta is called the oscillating factor. But now it is not simple harmonic. Okay, it is damped harmonic because we have the damping factor. I'm going to explain that as we proceed. The period of the oscillation is 2 pi divided by the imaginary part of our complex solution, and the imaginary part is omega root 3. So we have the period to be 2 pi divided by root 3 times omega. Now why is it damped harmonic? It is damped harmonic because as a motion carries on, the displacement, the maximum displacement, dies down to 0. We call the damping factor e to the negative omega t, and then the maximum displacement is simply a e raised to the power negative omega t. But as t tends to 0, as t tends to plus infinity, it tends to 0. So that is why it is damped harmonic motion. For simple harmonic motion, we see that the maximum displacement does not depend on time, so it stays constant as time elapses. But for a damped harmonic motion, though it is oscillatory, meaning cos of root 3 omega t plus beta is actually the oscillating factor, but now we have a damping factor which is e to the negative omega t, and a e raised to the power negative omega t is called the maximum displacement. And as time goes on, we see that the maximum displacement tends to 0 because it clearly depends on time. That's why it is a damped harmonic motion, and specifically we are going to say it is a weakly damped. Actually it is weakly damped. Now if the roots of your quadratic equation were real and equal, we are going to say it is underdamped. If they were real and distinct, we are going to say it is overdamped. Alright, we are moving on to question 3, which reads, it's on numerical methods. Okay, and the equation reads, the function y of x satisfies the differential equation dy by dx equal to f of xy, where f of xy is 2 plus y on x and y1 is 1. Use the formula y arrow plus 1 is approximately equal to y arrow plus h times f of xy, with h equal to 0.05 to obtain an approximate value of y1.1, giving your answer correct to 3 decimal places. Roman 2, use Simpson's rule to estimate the value of the integral from 1 to 1.1 of y dx. Alright, so let us analyze the equation together. First, we have to get the approximate value of y of 1.1. Remember that y of x satisfies the differential equation. So we have the given conditions. We have that f of xy is 2 plus y on x, and y arrow plus 1 is approximately equal to y arrow plus h times f of xy, and then our y1 is equal to 1. Okay, so from there we can get the approximation of y arrow plus 1 by replacing f of xy with its equivalents. So our y arrow plus 1 will be approximately equal to y arrow plus h times this quantity here is simply our f of xy. If you look at this approximation, that is, if you look at this approximation. So from here, let us start by getting the value of y when r is equal to 0. So we are going to get y1. So y1 will be approximately equal to, replace r to be 0, we have y0 plus h into 2 plus y0 divided by x0. But we have information that our y1 is equal to 1. It means that y of x0 is actually equal to 1. That is, when x is equal to 1, our y is equal to 1. So that can be our initial condition. So x0 is equal to 1, y0 is equal to 1. And should also recall that xn plus 1 is equal to xn plus h. H is called the step length. We are going to use this property when we proceed with the equation. So from here we can find y1 by just replacing our step length with 0.05, our x0 and y0 with 1 and 1. If we simplify correctly, we are going to get 1.15. And it should be noted that this value of y, which is approximately equal to 1.15, is simply the value when x is equal to x1. Remember that we are pairing x1 and y1, and remember that x1 is simply taking x0 plus the step length because of this formula. When n is 0, x1 will be equal to x0 plus the step length. Okay, and the step length is 0.05 and our x0 is 1. So it means that for x1 equal to 1.05, our y1 is 1.15. In similar words, we can say that y of 1.05 is equal to 1.15. But this is not our bus stop. We have to find the value of y when x is equal to 1.11. When x is equal to 1.1. And we clearly see that if we add another step length to 1.05, meaning if we add 1.05 to 0.05, which is the step length, we arrive at 1.1, and that is where we are going to end. So let's proceed. When r is equal to 1, we now get y2. Our y2 will be approximately equal to, we come here, we have y2 into when r is 1, so we have y1 plus h into 2 plus y1 divided by x1. So we have x1 and y1 already, and our h is constant. Okay, our y1 is 1.15 according to the previous response, and our x1 is 1.05. So it therefore means that our y2 is approximately equal to 1.304. So here, remember that here is supposed to be 1.15. so sorry for the error, but if you compute correctly, you're going to get your y2 to be 1.304. And it should be noted that this value of y2 is when x2 is equal to x1 plus h, and our x1 plus h is simply 1.05 plus 0.05, which is 1.1. So we can give a final conclusion that when x is equal to 1.1, our y is equal to 1.304, since we are to leave our answer to 3 decimal places. Now the last part of the equation is asking us to estimate the value of an integral using Simpson's rule. So first we create our table. We have xn and yn. When x is 0, when x is 1.05, and when x is 1.1, because we should have a step length, okay, meaning that the difference between the consecutive values of x is supposed to be constant, and for that to happen, then we need to be adding the step length to x, because the step length is already a constant value. So we need to leave from x equal to 1 to x equal to 1.1. So we need to add the step length 2 times. So we add it the first time and then we add it the second time. When x is equal to, when x0 is 1, our y0 is 1. When x1 is 1.05, our y1 here is supposed to be y1. Our y1 is 1.15, and when x2 is 1.1, our y2 is 1.304. Now the Simpson's rule says that this integral is h divided by 3 into the sum of the ends plus 4 times the sum of the odds plus 2 times the sum of the evens. How do we identify the ends? The ends are for y's, y0 and y2. Those are the ends. Plus now 4 times the sum of the odds. Remember I said here is supposed to be y1, and 1 is an odd number. That's why we say it is 4 times y1 only. There are no other terms inside. So we just need to replace the values of h, y0, y2 and y1, and then we compute to get the integral using Simpson's rule to be 0.1151. Alright, so we are left with two more questions. Question 4 is on oblique impact, and the question reads: a smooth sphere of mass 2 kg is moving with speed u along the horizontal floor when it collides obliquely with a smooth vertical wall. Just before impact, the direction of motion of the sphere S makes an angle of theta with the plane of the wall. After impact, S moves with a speed v in a direction making an angle of 60 degrees with the plane of the wall. The coefficient of restitution between the sphere and the wall is 1/3. Show that 1 tan theta is 3√3, 2 v is equal to u√7/7. Finally, find the magnitude of the impulse received by the sphere during the impact. Alright, so not to waste time, I already drew the diagram, so I'm just going to explain the diagram. So initially, here is before impact and here is after impact. So before impact, the sphere was moving in this direction because to the right is the direction of motion, but the initial speed of the sphere is u. It makes an angle of theta with the wall. So we need to resolve into two components, okay, because we are going to consider motion along the line of centers, meaning along the center of the sphere, horizontal line to the wall. So we resolve the speed into two. We have the horizontal component to be u sine theta and the vertical component to be u cos theta. Now after impact, we have that the sphere now moves backward, okay, because it was supposed to be moving to the right. So after impact, it now moves to the left. Now after impact, the speed is v and it makes an angle of 60 degrees with the plane of the wall. We also resolve into two components. We have a vertical component which is v cos 60, and we have a horizontal component which is v sine 60. Now this is our reference frame. It means that anything going to the right is considered positive, going to the left is negative, and going down is positive. That's the reference frame I choose. You can choose yours, okay. So we have to show that tan theta is 3√3. So the first thing to note is that the initial velocity of the sphere, that's the initial velocity of the sphere, is simply the sum of the horizontal and the vertical component, since it is a vector, okay. The speed is u, but the velocity is a vector quantity. So in the horizontal is u sine theta, so I, plus in the vertical is u cos theta, j, and downward is positive, to the right is positive. That's why I keep the positive signs. What about the final velocity of the sphere? The final velocity of the sphere, we have horizontally is now in the negative direction according to my reference frame. So it's negative v sine 60i, plus is still downward, so it is positive according to my reference frame. So I have v cos 60. So I've gotten the initial and the final velocity of my sphere. Now we need to analyze. The first thing to note is that the velocity of the sphere that is parallel to the wall remains unchanged because motion was to the right. So it means that we are only going to consider the velocities of that's the initial and final velocity of the sphere that is perpendicular to the wall. Anything parallel to the wall remains unchanged because motion was in this direction. So these components were not changing. So with that said, it means that u cos theta is equal to v cos 60, because this is the vertical component is supposed to remain the same at the end of the day. So u cos theta is equal to v cos 60 degrees. We can call that equation 1. Now the coefficient of restitution between the sphere and the wall is simply E, which is the difference between the velocity of separation divided by the difference between the velocity of approach. Since the wall was at rest, okay, it means initial and final velocity of the wall is 0. So we have in this direction, we have the final velocity of the wall, which is 0, minus the final velocity of the sphere. But the final velocity of the sphere in the horizontal direction has a negative sign. That's why we take 0 minus. Now we are going to consider only this component because we are dealing with the horizontal direction. That's our direction of motion is horizontal, and sine 60 is √3/2. So we have 0 minus negative √3/2 because of the negative sign. Now divided by the initial velocity of the sphere minus that of the wall. The wall was at rest, so its initial velocity is 0. The initial velocity of the sphere in the horizontal direction is u sine theta. So we can simplify, and we have that our coefficient of restitution is 1 divided by 3. So simplifying, we get our v to be u sine theta divided by 3√3. We can call that equation 2. Now we are going to look at these two equations keenly. Okay, we have equation 1, which is u cos theta is v cos 60, and equation 2, which is v equal to 2u sine theta divided by 3 root 3. So what we are going to do is that we are going to take equation 2 and fit in equation 1. So we are going to have u cos theta to be, in the place of v, I replace it with 2u sine theta on 3 root 3, and I multiply with cos 60. But we know that cos 60 is half, so here is the 2 in the denominator. The 2 in the denominator cancels with the 2 in the numerator. The u on the left hand side cancels with the u on the right hand side. We can divide both sides by cos theta, and then we multiply both sides by 3 root 3. In fact, this is just simplification. So simplifying, we get to the proof. Tan theta is equal to 3 times the square root of 3. Okay, now we have to also show that the final speed of our sphere is u root 7 divided by 7. So we come back to our first equation. U cos theta is equal to v cos 60 degrees. It means that cos 60 is half. Okay, we can multiply now the left hand side by 2, and we are going to be left with v here. So v will give us 2u cos theta. Now we can construct a right angle triangle because we know that this theta here is an acute angle. It is between 0 and 90, so we can have theta there. Now since tan theta is equal to root 3 times 3, and we know that tan theta in the right angle triangle is opposite divided by adjacent. It means the opposite is simply 3 root 3, and the adjacent is 1, because 3 root 3 is the same as 3 root 3 divided by 1. So h is a hypotenuse. So from the Pythagorean theorem, we have that the square of the longest side is the sum of the squares of the other two sides. Doing that perfectly, we are going to get our h to be the square root of 28. Now what is cos theta? Cos theta is adjacent, which is 1, divided by hypotenuse, and the hypotenuse is root 28. So we can rationalize, we get root 28 on 28, and we can simplify to get 2 root 7 divided by 28. Now from there, our velocity, our speed v becomes 2u into 2 root 7 divided by 28. Simplifying perfectly, we arrive at the proof that v is equal to u root 7 divided by 7. Finally, for this question, we need to find the magnitude of the impulse received by the sphere during the impact. So the impulse received by the sphere is just the mass of the sphere times the change in the speed, which is the mass of the sphere times the speed is v minus, remember speed is a scalar quantity, and the final speed was v and the initial speed was u. Okay, since we have already expressed v in terms of u, it means our final answer is going to be in terms of u. So our v is u root 7 on 7, then minus u. If we subtract well and we group like terms together, we are going to get that the magnitude of the impulse is equal to the magnitude of the that's the magnitude of 2u on 7 into root 7 minus 7. Root 7 minus 7 is negative, so the magnitude gives us something positive. So it means the magnitude of the impulse is 2u over 7 times 7 minus root 7. Alright, so I think the question is done. Let's go to the next question. Okay, the last but not the least question we have question 5, motion in 2 dimensions. It reads, a particle P moves with constant angular velocity omega on the polar plane with equation r equal to f of theta. At time t, the transverse component of the acceleration of P is 2a omega squared cos theta, where a is a positive constant. Initially, P is at a point with polar coordinates a pylon 2, 1, 2, 3, and 4, 1. Show that the radial component of the velocity of P is a omega cos theta, 2. Show also that dr by d theta is a cos theta, 3. Find the polar equation of the path of P, and 4. Find in terms of theta and omega the radial acceleration of P. Okay, so let's analyze the equation together. First, we have to show that the radial component of the velocity of the particle is a omega cos theta. So we begin with the given information. So we have the transverse component of the acceleration, and the radial component of the velocity is simply r dot, that is dr by dt. But the transverse component of the acceleration is r theta dot dot plus r dot theta dot. You can verify your formula booklet if you're in the hall and you're forgotten these basic identities. Okay, so we have that our transverse component given in the equation is 2a omega squared times cos theta. So it therefore means that 2a omega squared cos theta is equal to its identity, which is r theta dot dot plus 2r dot theta dot. But what do we know? We know that it was moving with constant angular velocity, meaning that omega, which is theta dot, is a constant. Therefore, differentiating it the second time gives you 0. That is differentiating the first time. Differentiating theta dot the first time is theta dot dot to give you 0, because theta dot is a constant. When we differentiate the constant, we get 0. So with that said, the transverse component of the acceleration, which is the left hand side, is just equal to 2 arrow dot times omega, because theta dot here is omega. This component becomes 0 because theta dot dot is 0. From there, we can divide all through by 2, and then from there we also divide all through by omega. Dividing all through by 2 and all through by omega, we get arrow dot to be a omega cos theta. But arrow dot is the radial component of the velocity, so we have proven. Now the next part is asking us to show also that the arrow by d theta is equal to a cos theta. So we pick up from the previous proof. Arrow dot is the arrow by dt, and by the chain rule, the arrow by dt is the arrow by d theta times d theta by dt. Okay, so we have that our arrow dot is equal to the arrow by d theta. Our d theta by dt is simply omega. So with that, our d arrow by d theta becomes arrow dot divided by omega. Remember, we need to find the arrow by d theta. So the arrow on d theta is arrow dot divided by omega. But we know what arrow dot is. It is a omega cos theta, because you have just proven it. Divided by omega, it simplifies to a cos theta. Question 3, we are asked to find the polar equation of the path of the particle P. Here we are going to use integration. So in the previous proof, we have proven that the arrow by d theta is equal to a cos theta. So we can separate variables because we need the polar equation, meaning we need r to equal to f of theta. And here we just need to separate variables and we integrate both sides. Now integrating the left hand side, we get r. Integrating the right hand side, we get a sine theta plus a constant of integration. Now we need to apply the initial condition, which says that the particle was at a point a pylon 2, meaning that when r is equal to a, our theta is equal to pylon 2. We can get the constant of integration as 0 because sine pylon 2 is 1. You have times a, so a minus a is 0. So with that said, it means our r is equal to a sine theta is the polar equation of our curve. And finally, we need to find the radial acceleration of the particle. The radial acceleration is given by r dot dot minus r theta dot squared. Now we need to find those various components. Let's begin with r dot dot. Note this transformation very well. R dot dot is equal to d by d theta of d r by dt times d theta by dt. So this is equivalent to d by d theta. Here is supposed to be theta. D by d theta. Our d r by dt is r dot, and we proved that it was what? A omega cos theta. Then we multiply it with d theta by dt, which is omega. Now if we differentiate here with respect to theta, like I said, here it's supposed to be theta, not r. Sorry for the error. If we differentiate here, we have negative a omega sine theta. Multiply with omega, it becomes negative a omega squared sine theta. So with that said, our radial acceleration is given by r dot dot, which is this, minus r, which is a sine theta, as we have here, times theta dot squared. Our theta dot is omega, so theta dot squared is omega all squared. If we simplify perfectly, we get that our radial component of acceleration is negative 2a omega squared times sine theta, and the equation is done. Alright, the last question is on rotational dynamics, and here we are going to end the video with this question. Okay, the last two questions you can try your best there, but the last question is actually on probability, and I'm going to upload a link of a similar question that I solved already in the channel. And also the question 7 is on motion in a resistive medium. I'm also going to upload a similar example that I solved. So we are going to end this video with this question. It reads, show by integration that the moment of inertia of a thin uniform circular disk of mass 2m and radius a about an axis through the center O of the disk and perpendicular to the plane of the disk is ma squared. The disk is free to rotate in a vertical plane about a smooth horizontal axis through a point A on the circumference of the disk. The axis is perpendicular to the plane of the disk. Roman 2. show that the moment of initial of the disc about that axis is 3ma squared. The disc is released from rest when AO is horizontal. Show that 3a d theta by dt all squared is equal to 4g sin theta, where theta is the angle that AO makes with the horizontal through A. Find the components of the reaction at the axis perpendicular to AO when theta is equal to pi ln 4. Okay, so let's begin with showing by integration that the moment of initial of this disc about an axis that is passing through O and perpendicular to the plane of the disc is ma squared by integration. Okay, so first we consider the disc is a circular lamina. Okay, so we have the axis which is passing through the center of the disc. The radius of the disc, it means the distance from any point to the center of the disc, is A. Now that's the center of the disc. Okay, so what we're going to do is that we are going to choose an increment on the we are going to choose an increment. So step 1, we choose an increment. Here is a diagram already. So step 1, we need to choose an increment, means we choose a small portion of the disc. We can describe that portion. It has a very tiny mass delta m, and then the length of the portion, because the portion is somehow rectangular. Okay, so the length of the portion is 2 pi x, and then the width of the portion is delta x. From there now we can get the area to be 2 pi x delta x, length times width. Okay, so start by letting lambda be the mass per unit area of the disc. It means lambda as well will be the mass per unit area of every increment that we take out from this disc. It is a constant. So with that said, lambda is equal to the mass of the disc divided by the area of the disc, which is the same as the mass of the increment divided by the area of the increment. So from there we can get that the mass of the increment is multiply lambda with 2 pi x delta x. We get this. Now let us find the moment of initial of that increment. By the definition, the moment of initial of that increment is simply the mass of the increment times the square of the distance that is separating the axis and the increment, which is x squared, after squaring the distance. Now we need to replace our delta m with 2 pi lambda x delta x. We multiply with x squared. We bring like terms together. We have that the moment of initial of that increment is 2 pi lambda x cubed delta x. Now if we take all increments on the rod, our delta changes to d, so we now take a total derivative. From there now we need to get the moment of initial of the disc, so we integrate both sides. 2 pi lambda is a constant, then we need to integrate with respect to x. The x is simply kind of a radius, okay, and it is between 0 and the radius of the disc. The radius of the disc is a, and we are integrating x cubed. Integrating x cubed, we have x to the power 4 on 4 from 0 to a. We impute the limit, and then we replace the value of lambda with 2m over pi a squared. Remember, it's a mass which is 2m per unit area. The area of the disc is pi radius squared. The radius is a. If we simplify perfectly, we are going to arrive at the proof that the moment of initial of this disc about the axis passing through the center and perpendicular to the plane of the disc is ma squared. Now the next question is asking us to find the moment of initial, or proof that the moment of initial of the disc about an axis through A is 3ma squared. Now this axis through A is simply a point on the circumference of the disc, and the axis through A is perpendicular to the disc. So let us redraw the diagram. So we have the axis that is passing through the center, and then we have the point on the circumference of the disc, which is at the point A. Now the distance that is separating these two axes, delta and c, is simply the radius of the disc. Remember that the two axes are perpendicular to the plane of the disc, so it therefore means that they have to be parallel to themselves, because both of them are perpendicular to the plane of the disc. Now we are going to use what we call the parallel axis theorem to find the moment of initial of this disc about the axis passing through A. That theorem says that the moment of initial of the disc about the axis passing through A is equal to the moment of initial of the disc about an axis passing through the center plus the mass of the disc times the square of the distance separating the two axes. From there, we have already gotten that the center of the moment of initial of the disc about an axis passing through the center is ma squared. So we need to add it to 2ma squared. 2m because it's the mass of the disc. A squared is the square of the distance separating the two axes. If we add it up, we get that the moment of inertia of the disc about an axis passing through A, which is on the circumference of the disc and perpendicular to the plane of the disc, is 3ma squared. Alright, finally, though I already drew the diagram for the second part, we're being told that the disc is released from rest when AO is horizontal. So AO is horizontal. This is the initial case. It is at rest. Now it is now rotating in a vertical plane. So here's my direction of rotation. The angular velocity is omega. Now AO makes an angle of theta with the horizontal through A. Okay, so the horizontal is through A. That is it. And then AO, here is it. It makes an angle of theta with the horizontal. The distance from A to O is simply small a. It's the radius of the disc. It does not change. Now, to actually prove that in ensuing motion, the equation of motion of the rotating body is given by this, we have to apply what we call the principle of conservation of mechanical energy. It says that the initial mechanical energy of the system is equal to the final mechanical energy of the system. Knowing fully well that the mechanical energy of the system is the sum of the kinetic and the potential energy of the system. So initially we need to sum the initial kinetic and potential energy of the system. Kinetic energy is half mv squared, okay, but since initially was not rotating, it is 0. The potential energy is mgh, where h is the distance of the center of mass of the system to the line of 0 potential energy, meaning that to the horizontal line. So it is also 0 because initially it was at rest. Now what about the final mechanical energy? It is simply the sum of the final kinetic energy and the final potential energy. Now, what is the final kinetic energy? Now, since we are dealing with rotational motion, okay, that's rotational dynamics, we cannot write kinetic energy as half mv squared. We need to write it in terms of the angular velocity and the moment of inertia. If you watch the previous videos I did, you're going to understand this concept better. So the final kinetic energy is simply half the moment of inertia of the system about the axis that is passing through A, which is the axis delta, times the square of the angular displacement. The square of the angular velocity. That's the final kinetic energy. What about the final potential energy? It is the mass of the system, which is 2m times g times h. Like I said, h is the distance from the center of mass of the system, which is definitely at the center, to the line of 0 potential energy. So you can clearly see some kind of right angle triangle here, which you can use sine theta to be opposite h divided by hypotenuse, which is a. So from there, our h becomes a sine theta. And since this h is actually a distance that is below the line of 0 potential energy, it is considered negative. So from there, we have that the final mechanical energy is half times the moment of inertia of this disc about an axis passing through A has been proven to be 3ma squared, and then we multiply it with omega squared. We add it to 2mg, and then we multiply it with negative a sine theta. I repeat, the negative sign is because the distance we are taking is below the line of 0 potential energy. From there, we apply the principle again, which says that the mechanical energy initially is equal to the mechanical energy finally. Meaning that adding up here, we have initial is 0 to be equal to final. We just try to simplify terms and we arrive perfectly at the proof. So we have proven that in ensuing motion, the equation of motion of our rotating body is 3a d theta by dt all squared, which is omega squared, equal to 4g sine theta, where theta is the angle that the line AO makes with the horizontal passing through A. Finally, we have to find the components of the reaction at the axis that is perpendicular to AO when theta is pi on 4. So we need to impute the reaction. So we have a reaction that is in the same direction as the disc. We call it the radial reaction. And we have a reaction that is perpendicular to the disc. So we call RX and RY. Now, we need to also indicate the forces that are acting on the disc as well. We have the weight, which is 2mg. Then we have to resolve this weight into its components. We have a component that is perpendicular to the disc, is 2mg cos theta, and a component that is parallel to the disc, we have 2mg sin theta. Now we have the acceleration in that direction, so be the transverse, and in the other direction to be the radial. Now we have to apply the Newton's second law of motion, and here we are concentrated on resolving transversely, meaning we need just the perpendicular component, so we resolve like this. Resolving transversely, we need to take the resultant force and we equate it to the mass times the acceleration in that direction. The resultant force is simply 2 mg cos theta minus rx equal to the mass, which is 2m, times the acceleration in that direction, which is the transverse acceleration. But in the previous question, we just saw that the transverse acceleration is r theta dot dot plus 2r dot theta dot. What is r? r is the distance from the center of mass of the system to the axis, and it is simply small a. Now, since we have seen that our r is a and a was called a positive constant, then we can see that our r dot is 0 because we are differentiating the constant. So with that said, r dot being 0, this quantity goes to 0, and we have the transverse component of the acceleration to be r theta dot dot. So from there, we just need to replace it here, okay, and then we need to replace our arrow. In fact, if we find rx, okay, and then we replace, remember that we have to replace our arrow with our a, because r is the distance from the center of mass of the body to the axis. So we have rx to be 2 mg cos theta minus 2ma theta dot dot. How do we then get theta dot dot? We need to differentiate the equation of motion of the body. The equation of motion of the body is dA d theta by dt all squared to be equal to 4g sin theta. We differentiate both sides with respect to time. If we differentiate the left hand side with respect to time, we drop the power, we have 6a. We differentiate the interior, we get d squared theta by dt squared, and we multiply it with d theta by dt to the power 2 minus 1. If we differentiate the right hand side, we get 4g sin theta and then d theta by dt. That is the chain rule, since we are differentiating a function of theta with respect to time. Now the d theta by dt on the left and the right hand side will cancel off, and then we can find theta dot dot. So you are supposed to now look for d squared theta by dt squared from here. You find rx by replacing it here, and then now you replace theta with pi on 4 to find rx when theta is pi on 4. So thank you guys for watching, and I wish you all the best in this year's examination.